Hello Algebra 2. Today we're going to continue reviewing parabolas by looking at their properties. I think pretty much all this information was stuff you saw in Algebra 1, so this is going to be a quicker version of what you already did in Algebra 1. We'll see if there's anything new. I really don't think so. So parabolas come in a variety of forms. There's the standard form, there's the transformation form, which we worked with in the last lesson where we've shifted them right and left and read inside versus outside and all that good stuff. You also have the standard form or the polynomial form, which is real common to see parabolas in, perhaps even more common. So one of the things we'll learn to do is change one form into another. So the form I'm talking about today in this lesson is going to be the polynomial form, and that's this one, ax squared plus bx plus c. This is what a parabola looks like if it's in polynomial form. Just to review from the last lesson, you might try to write down an example of a parabola in transformation form. I'd try to pause the video right now and write down an example of a different parabola in that form. So transformation form, I'm just going to review with you, is something like f of x or y equals some number out in front, let's call it a for a stretch or compression, and then you have like x minus some left or right sometimes, and it's squared for the parabola. And then you have plus or minus something outside sometimes, which takes it up or down. So there's the transformation form that we worked with in the last lesson and that we'll continue working with extensively this year. Today, though, we're going to focus on this guy, the polynomial form. So let's talk about a variety of things with the polynomial form of a parabola. When does it open upward? You should remember, one of these coefficients, a, b, or c, controls when it opens upward, and that is a. If a is positive, it opens up. So positive a's will open upward. That's how you write that with an inequality. If it opens downward, it's going to be the opposite. That a coefficient would have to be negative for it to open downward. Why don't I have equals 0? A equals 0? Well, of course, if a was 0, then it'd just be bx plus c, which is like mx plus b, which is a line. That wouldn't be a parabola. Okay, yesterday I think we talked about the y-intercept, so let's go over that again. Whatever form you're in, whether you're in polynomial form or the transformation form I just erased, to find the y-intercept, that's where you plug in 0. So how do you write that? It's going to be f of 0, and written as a point, let me just write that in red. How I'd like to see this is 0, and whatever f of 0 turns out to be, the y value. The vertex of a parabola is kind of obtained from an interesting place. When we get to reviewing the quadratic formula, I'll derive that for you again, and it should really make sense. But from last year, hopefully this sounds familiar. The vertex of a parabola is going to be, I said write it as a point here, so let's do that. It's going to be b over 2a, negative b over 2a. And so if you want the y value, of course, you'd plug that in and go f of negative b over 2a. So that's the vertex of a parabola, and that's the vertex form when, of course, you're in polynomial form. I think there's a couple problems in your assignment that are going to be in transformation form. If it's in transformation form, it's real easy to read off the vertex. You don't have to do any of this negative b over 2a jazz. You just say, well, left, right, up, or down. That'll give you your vertex. Much easier in transformation form. So, key is to remember here that x equals negative b over 2a. Where does that come from? If you don't remember from Algebra 1, I'll be showing you in a lesson or two down the road. The axis of symmetry is going to go through that same spot. Let's just draw kind of an arbitrary parabola in the first quadrant here. So here's an arbitrary-ish parabola, which doesn't even have any zeros or x-intercepts. Here's its vertex. So 1, 2, 3, 4, 5. Looks like this guy's about 5. 1, 2, 3, 4. Yeah, it looks like that's about 4. Where's its line of symmetry? Mine looks a little lopsided, but that's going to be the line of symmetry. So the line of symmetry is clearly a vertical line. Vertical lines, are they x equals or y equals? Think about it for a second. You should realize that all the x values on that line are the same, so it's x equals. And that line goes through the vertex, in fact, right? If I actually drew it perfectly. And it's symmetric across both sides of that line. So it should be x equals negative b over 2a, the same x value as for the vertex. So when you do negative b over 2a, you're really finding two things. You're finding the x value of the vertex, and you're finding what you need to write down the axis of symmetry. That's what this acronym means here, axis of symmetry. Okay, let's apply what we've learned so far to an example or two. So here's a parabola. I think it's in standard polynomial form. So we can't just read any shifts or stretches or anything like that. We're going to have to actually go through these procedures, and we'll try to come up with a graph. So one step at a time. First, is it going to open up or down? Well, A tells you if it opens up or down. So this guy is going to clearly open up. That's because 2 is positive. What's next? Well, it doesn't matter which order you do these in. Let's find the y-intercept. So the y-intercept is going to be 0, but, bless you, if I plug in 0, what do I get? Well, you could do scratch work if you need to. This is pretty easy. If I put 0 in, it goes there and there. Those guys get wiped out, and I get 5. So this one has a y-intercept of 5. Next step is to find the vertex, or the axis of symmetry. You know, I'm just going to find the axis of symmetry first, and then we'll worry about the vertex. So x equals negative b over 2a. Remember, it goes a, b, c. If you're not real clear on that, make sure you put those letters over the coefficients. It's not the variables, it's the coefficients, the things attached. So I'm going to go negative, and b is negative 4. All over 2 times a is positive 2. So that's going to be 4 over 4, which is 1. That's the axis of symmetry. I think I've got enough information to start graphing this guy. So I'm going to go over here and start graphing it. So let's see. We've got an axis of symmetry with the line x equals 1. So that's going to be right there. I'm going to draw my dashed line right there. I know it's opening upward, so it's somewhere like this along that axis of symmetry. And I know its y-intercept is 0, 5, so I'll get that guy. 1, 2, 3, 4, 5. So the only question is, where on here is it? It must be somewhere in here. Depends how steep it is, I guess. This is really too steep, so it's pretty steep, but not super steep. So we still need to find the actual vertex. So the vertex, we already know, is going to have an x value of 1, because it's somewhere on that line for the axis of symmetry. And how do you find the y value of any point? Well, you plug it in, right? Or you can go back over here where it says f of that vertex. Don't let this notation scare you. It's just plugging that point in. So I might need a little scratch work here. So I'm going to go f of 1. Maybe I'll do it in green just to mix it up. So f of that 1 is going to be what? 2 times 1 squared minus 4 times 1 plus 5. So that's going to be 2 minus 4 plus 5. That's 7 minus 4 is 3. There we go. So the vertex is at 1, 3, 1, 3. That looks good with my y-intercept that I have, and I think I'm good to go. I've got a graph. If they ask you for a third point on the graph, you've already got one ready-made for you. If this was 1 that way and it was up 5, then out 1 this way should also be that same thing. So we have another point here that is 2, 5, since I went 1 that way and 1 that way. Parabolas are perfectly symmetric, so use their symmetry to your advantage. Let's look at a couple more examples. So I'm going to do the same thing with this function. Here's a second example. And then let's just vary basically what kind of things they could be asking us for. I think we're going to use all the same information, but they might ask us a couple different questions. So we might be asked something like this for a third example. So let's say we have this function, this parabola. And let's say they want us to find the max or min, and they want us to find the domain and range. Okay, so let's go through the same procedure on function or parabola g. I'm going to go a little bit quicker this time. You guys have seen this before. So, there is the negative. In fact, it wouldn't really matter if I had this switched around, right? Let's switch it around a little bit. Let's say it had said 3 minus 2x minus x squared. Does that change the function? Well, of course not. This guy is still opening downward. And it's not because of the 3. A is actually negative 1 over here. B is negative 2, and C is this 3. So if it's turned around, you can either turn it around yourself or just be alert. So this guy's going to open downward because negative 1 is less than 0. What's its y-intercept? Let's find g of 0. 3 minus 2 times nothing minus nothing squared. It's going to be minus nothing squared is nothing. So we've already got a point on the graph is 0, 3. Sweet. Next I want to find my vertex, so I'm going to say that's going to be x equals negative b over 2a, which is going to be 2 over negative 2, which is negative 1. That's my axis of symmetry also. So my axis of symmetry on this guy is over here at negative 1. Label it. I know it goes through 0, 3. And I know it faces downward, so it's going to be something like this. The vertex must be somewhere up there. Where exactly? Plug this guy in. So g of negative 1 works out to be, lots of negatives here, very careful. So I'll use a different color. It's going to be 3 minus 2 times negative 1 minus negative 1 squared. Order of operations. Exponents first. That's negative 1 squared is positive 1. This is chillin'. Negative times negative is positive. That's 5 minus 1 is 4. Let's see if this makes sense with our picture. I think it sure does. That's going to be down. Everything's checking out. So here's the parabola we were asked to graph on this one. Do I have the x-intercepts? No. I showed you guys how to do that the other day. I think you might need the quadratic formula in a couple of these though, so don't feel pressured to do the x-intercepts unless they ask you to. H of x, how are we going to do that one? Well, we have some different questions. Same kind of parabola. This time they said find the max or the min, find the domain and range. I think domain, range, max, min, those all depend on the vertex. If you think about this picture over here, the domain's going to be everything, because that's all the x values on the curve. The range is going to be negative infinity up to the top. And ask yourself, is this a max or a min? Well, it's clearly the biggest thing on the curve, so it's a maximum. How about this problem? Well, I think we just want to sketch it. First, let's find the vertex. So we'll go negative b over 2a. So negative, there's b, 2, there's a. It's going to be negative over negative is a positive 2/6, which is 1/3. It worked out as a fraction this time. That can, of course, happen. So I know the axis of symmetry is at 1/3. So let's see. Something like that, if this is 1. And I'm going to plug it in to see what my y value is on the vertex. So where's it going to be? 1/3. Let's see. So we're going to have to do some math on this one. 1/3 squared, 2 times a third, minus 4. Let's simplify that. Square the top and the bottom here. You multiply a number times a fraction by thinking of a 1, right? So 2/3 minus 4. That's negative 3/9 plus 2/3 minus 4. You need to combine fractions like that by using a common denominator. On this one I see that that's a third though, so I'm going to say that's negative 1/3. Now I've got thirds here, so all I need to do is change this into thirds with my good friend the clever one. So now I've got all thirds, negative 1 here, 2 of them here, minus 12 of them there. That's negative 13 plus 2 is negative 11 thirds. So that's the y value of the vertex. Let's go plot it over here. Negative 11 thirds is like 3.67. So 1, 2, 3, 4. It's going to be something like that, between negative 3 and negative 4. Now you want to ask yourself, is it going up or down? A tells you that. That says down. So I'm going to be going down from there, something like this. And now I think with that picture, that little sketch, it's not a great picture, but it's good enough to answer the question. Max or min? And what is it? Domain and range. Well, look at that. Do you have a maximum green value or do you have a minimum? Well, clearly this is a maximum. So I'm going to say we've got, and you want to write it just like this, we have a max of that. That's the highest it gets, that negative 11 thirds. And where did it happen? Which occurs at x equals 1/3. So write what it is and where it happened. The other thing you want to do is the domain and the range. I should probably just label that point. Let me do that. So this point, remember, is 1/3 negative 11 thirds. Domain and range from a picture like this should be super simple. Remember, domain is all the x values that exist on the curve, all the x values that make it work. This guy keeps going out. All parabolas do that, hint, hint, hint. So you can plug in any value from negative infinity to infinity into them. The range on this parabola is going to be, it's going down forever, so you always want to go bottom to top. So the bottom is negative infinity. You can never quite get there. That's why it gets a parenthesis, remember? And you're climbing up and up and up until you get to the top of this hill at the maximum y value of negative 11 thirds. Can you actually get there? Yes, you can if you're exactly 1/3. So this is a bracket. So there you go, a little review of parabolas and their features when they're in polynomial form especially. I'll see you next time.